Right, so let's get started. So today we will finish the lecture to 4, which was about stereo reconstruction problem. Right, so let's briefly review what we've done so far. Okay, so first of all, we redefine the epipolar geometry. In epipolar geometry sharing, point x1 in the left images or image 1 must be located on the epipolar line, which is denoted by L2 tilde. This will reduce the correspondence reach to the much simpler 1D problem. Something like this. But when we just consider such a original epipolar line, so it's not just the horizontal to the baseline. So maybe it requires some x direction and y direction disparity map. So in image rectification, we just rectify to make the both camera face exactly same direction. So here, so in epipolar geometry, in image rectification, we define a new matrix R consists of R1, R2, and R3 as a row vector. R1 is kind of the T over T, length of T. So it means the direction of the translation. And R2 is the another perpendicular vector, which can be determined by cross product 0, 0, 1 transpose and R1. R3 is another perpendicular vector, so R1 is going to be R1, R3 is going to be R1 cross product R2. Then such a matrix R transform, the rotate original blue plane to this such a red plane. So that's the process of the rectification. Here's the example. This is original input images, left and right images. But when you just consider this single pixel, epipolar line should be like that. But when you just rectify original image to the such rectified images, epipolar line parallel each other and horizontal horizontally, I'll say, parallel each other, right? Horizontally parallel each other. Right? Disparity explanation problem, just like the disparity between some pixels in the left images and corresponding right pixel images in just x direction in these images. Okay, so yeah, this is a colored disparity map. Because of this disparity defined in a pixel space, but we are interested in the depth information. The physical depth, meaning of the depth. So we have to consider how to convert disparity to the depth images. Depth map. So we also consider another singular triangle. Similar triangle. This triangle and this triangle. Then finally, we can just get the very simple equation z is equal to f times p over t, where g was the depth, f was the focal length, and p is baseline, t is disparity. Because the focal length and baseline predefined or pre-computed during the calibration, we just convert depth to disparity or disparity to depth by using such a equation. Right, so and we also discussed how to find the correspondence between two left and right images. So this is kind of the matching problem. So we can define a matching similarity measure, patch similarity measure, then design a matching score. Then when we just consider a whole pixel and the pixel level matching cost, it's going to be the cost volume, whose size it was h by w by delta d. So one of the very popular similarity metric was the ZNC. Of course, before the deep learning area, data-driven method, ZNCC is kind of the cross product. I mean, the normalized vector cross product. Another one is SSD. 그쵸? SSD. Some of these care difference, right? So this is one of the examples of the Bullock matching. So because of this is a stereo matching problem, it inherently have some occlusion region like this or this. So and in Bullock matching method, we have some kinds of the assumption. For example, front of parallel assumption, which means each plane in the images should be frontal face. So we just assume this every pixel in this window move similarly. I mean the exactly same, but in rare cases, which are often invalid, right, or violated. Something like the slanted surface case, like this one. Slanted surface case. Another violation was the disparity discontinuity, right? So because the pixel moves differently depending on disparity or depth. Okay. So in left-eye consistency check or the task, outlier or the hypoconstant can be detected. Then compute disparity map. To do this, compute disparity map for first images and verify if they map to each other, like the cycle consistency. Then just fit out occluded region by using some kinds of post-processing like the filtering or something like that. Right, so that was the Bullock matching method. But now we have a very, very good data-driven method, something like the deep learning. So after deep learning evolution, most of theoretic methods have been formulated to reformulate theoretic problem or Bullock matching problem within a deep convolution neural network or just deep neural network. This is kind of the CMS model or CMS network. So the first attempt for the stereo matching has been proposed in this paper, stereo matching by training the convolutional neural network to compare image patches. As you can imagine in the title itself, the comparing image patches with the training convolutional neural network means they want to reformulate patch similarity measure with a deep convolutional neural network. In other handcrafted features or similarity metering like ZNCC or SSD do not take into consideration all relevant geometry or line-metry invariance or Euclidean pattern. Of course, we can give somehow invariant to the geometric deformation or photometric deformation, but it's really hard to design a whole of kinds of deformation by hand. So in data-driven method or the deep learning method, matching cost computation can be treated as an image classification problem. People that the word is too complex to specify this by hand, so matching cost can be treated as an image classification. I mean, we can reformulate matching cost computation as a learning problem, something like this. So let's suppose that this is one of the patches in the left images, and this is one of the corresponding patches in the right image. So when you just consider the center pixel, and if we have ground truth data, we can just say, right, these two patches are good match or positive patches. And if there's one patches in the left images, but there's another patches in the right images, but it's not a say corresponding one. I mean it's if it is a bad match case or negative patch case, then this is kind of image classification problem. It means that input is a two. I mean the pair of the patches. Output is just kind of binary label like the positive or negative. Then we are going to formulate good classification network to classify these two patches, positive or negative, good match or bad match. So this is the kind of the deep learning based model for the set matching problem. So this is called star matching by training the convolutional neural network to compare image patches, which is called the MCCNN, for example. So, in other words, they tried to train a CNN patch-based, patch-wise, based on images with a ground truth disparity map. This is kind of ground truth data from the Kitty data set. You can just check the full public data, which is the one of the popularly used public data set in Ceramic problem. Anyway, this is kind of the left images. Of course, there is another corresponding right images, and this is the I'll say one of the examples of the ground truth depth map, which is measured by LiDAR sensor. That's why the measured depths are very sparse. Anyway, so this very, even though this is colored, even though this is visualized, some color scale, but this, anyways, this is kind of the grayscale value. Anyway, so this very map represent, for example, this pixel moves to, let's say, 5 pixel, or this pixel move to the 10 pixel or something like that. So it means that this is kind of ground truth data. Then we are going to just define such a training data to train matching network. So in other words, calculate the features for each of the two images using the random model. Then correlate the feature between the two images. I mean compare the features, pairwise features between the two images. For example, by using the dot product, then find the maximum for every pixel, which was called the winner take all, or just learn the global optimization to find out, I'll say, optimal disparity map. This is overview of the FCNN. So from now on, let's talk about the model itself. In original FCNN paper, they proposed the two variant of the model. First one is the London similarity, or first model was called the accurate model, accurate version. And the second one was called the cosine similarity, which was called past version. Anyway, in first case, when we have the left patches or right patches, they may be corresponding or not. So this is going to be the binary classification problem. So in first case or non-similarity case, first of all, we just extract the good feature vector, let's say, from the left image or left patch and right patch, right? And then concatenate each other. Then by using additional MLP or FC layer, finally determine these two two features are similar or not. Because we already have the ground truth data like this one, then we can finally train whole network. Of course, these networks shared each other. So that's why this kind of model is called a kind of Siamese network. 그쵸? In Korean 샴쌍둥이 뭐 할 때 시아메즈 그 시아메즈예요. 그래서 shared로 피처를 뽑아서 이제 MLP를 달아서 similarity 매저한다. 그래서 이게 learned features and similarity metric or similarity metric or similarity measure. So this is accurate. This is kind of accurate, but it potentially more expensive because we have to h by w by t times MAP evolution. I mean the evaluation of the similarity metric. So it's going to be really slow. This is the first version. In cosine similarity case or the fast version, however, given two patches, left patches and right patches, they just extract the feature vector independently with shared network, right? But in this case, we directly compare feature, let's say feature 1 and feature 2 with dot product. Then measure similarly as 1 or 0. So in this case, we don't have any similarity metric. I mean we don't have any MLP for the similarity metric. So it means that because of their whole fully convolutional layer, even though these two models, I mean this network, convolutional networks trained on patch level, at testing time, when we have the two original images, let's say image 1 and image 2, these two, patch 1 and patch 2, anyway, first of all, at testing time, we directly apply this convolution layer to the original image itself, then extract the picture map, not just picture, one single picture, but picture map. Then just compare the similarity by using the dot product. Then, which means we can drastically reduce the complexity comparing to this one. So, ideally, by using such a model, we directly compute feature map with single feed-forward, single feed-forward neural network. So, in other words, learn features and apply the dot product directly. So, features must do heavy lifting. So it's going to be really fast. So that's why left one is called the accurate version, right one was called the fast version. So the remaining question is how to train such a model. So first of all, training set is composed of the patch triplet. WL of XL left or left plus, WR of XR negative, WR XR positive. So let's say this is image L and this is image R. WL is the one of the image patches, and XL reference is kind of the also location. And XR means kinds of patches in the right images. And when we already know the positive or negative location, I mean the ground truth disparity map, then for the positive case, the special location is going to be XR pose, or for the negative case, it's going to be the XR neck or negative case. This is kind of setting. I mean, given left and right images and disparity map or depth map, we are going to make such a patch triplet, which can be used to train a stereo matching network like this. So sum of XL of WL of XL is an image patches from the left images centered at XL, which consists of small xl and YL. WR of XR is an image patches from the right images centered at XR is equal to small xl times YR. Negative example, for example, XR neg can be determined by something like this. XL left negative T, where this is the ground truth disparity. The truth disparity. For XL left, and by adding the sum perturbation, in this case just offset O negative, drawn from the somehow say uniform distribution from negative n high, which is usually 6, or negative number of high or number of low, which is often called 3, or plus number of low or plus n high. Then this kind of offset can just make us a negative point, negative x point. This is negative example. For the positive example case, XR pose can be determined by XL left minus F. It's just that, but by perturb very small, I'll say, pixel, very small scale pixel, let's say O pose, which are drawn from the negative P high to the plus P positive P high, where Pi is just 1. So it's going to be just like negative 1, 0, 1. So this is just like the positive sample. Okay, so here these denote the truth disparity for the pixels provided the ground truth data. So usually we just set n low as a 3 and high as a 6. So this is kind of hard negative mining. So it means that when they increase the number of NH, let's say 100 for example, then that sample, I mean when NHI was 100, that sample is going to be really easy negative sample. But by just considering those nearby patches as a negative pixel or negative patches, we can just give the high discriminative power to model. So this is kind of the hard negative mining. So this is kind of example. This is right images and this is target images. Let's suppose that there is the corresponding patches in the left images, and here was the original Excel left, but and we already have it should be moved to the to left direction with the D pixels, which is the berry. Then positive sample should be located as this pixel, or just this pixel or this pixel. When you enlarge each corresponding pixels, they are similar but slightly different. So we can just say these three kinds of patches are positive examples. Positive examples. So by considering the corresponding patches in left image patch, for example, left images and one of the positive examples and one of the negative example can just can be defined as one of the frame example. And this is just a positive sample, and for the negative sample, we just consider the nearby pixel, which is defined like this. So during the training, given a left patch, maybe it should be like this one. It should be similar to the positive example. But during training, we have to train a model to make these left patches and right positive patches pull, while left image patches negative example patches push each other. Pull and push. So this is kind of patch similarity learning problem. Right. So this is training samples. Then finally, we need some loss function to train the model with such a triplet dataset. In original MCNN paper, or the string matching by training a convolutional neural network to compare image patches, they just use a hinge loss defined like this. L loss is equal to maximum 0, m. M is constant. M is constant. S minus. S minus is kind of, squares of the network for the negative example. S plus is going to be squares of the network for the positive example. S minus and S plus. So square of the network for the negative case, square for the network, square of the network for the positive case. So it's like the output of the network. Then, by minimizing such a loss, the loss is going to be 0 when similarity of the positive examples is greater than similarity of the negative examples by L is the margin M. Again, loss is going to be 0 when the similarity of the positive example, let's say S plus, is greater than similarity of the negative example S minus by N is the margin M. Then, because due to the max operation, it's going to be 0. So after loss is equal to 0, there's no backpropagation happen, right? So this prevents the separation of positive and negative features that are already well separated. Right? So in a geometric manner, if we have a query patches, let's say WL, and let's suppose that we have a positive patches and negative patches here. By minimizing hinge loss, we want full XL and XR pose feature, while push XL and XR neg features, and if the similarity of the positive case was the S plus, and similarity of this one is X minus, then if S plus is greater than the similarity of negative example by at least a margin n, I mean if X are negative samples far enough, there's no more reason to push each other between XL and X are negative. So that's the reason. So in other words, which give the models the capacity to focus on the hard case, not just simple case. I mean the easy case. The margin n is the tunable hyperparameter. The paper just used m is equal to 0.2. So when you just draw the such say loss graph, it should be like that. So again, L was equal to maximum 0 or 0, m plus s minus s plus. So for example, in this case, if s plus is equal to negative 0.4, then when we just consider x-axis as s minus, when s minus is larger than negative 0.6, the loss should be looks like this, because it is larger than 0 in this case, right? Otherwise, if the s negative is smaller than negative 0.6, let's say if this term is smaller than 0, it should be always 0 because of max operation. So the loss graph should be looks like this. In other words, during the training, S negative, I mean the just S minus should be moved to the this direction to minimize the loss function. Then the S negative will be decreased. So when we define S plus as a 0 or S plus as a 0.4, it just move like this. Similarly, when we just define negative S, when we just have negative S negative as a 0.4, when S plus is smaller than negative 0.6, it should be like this. Or if S plus is larger than 0.6, it should be always 0. So it means that during the training, we have to increase S plus, right? We have to increase scores for the positive sample. So by minimizing such a loss function, we can increase the scores of positive sample case while decrease the scores for the negative case. So this is the hinge law. Right, so that's it. So this is just a similarity measure. So in stir matching pipeline, after build, cost volume, for example, H by W by T, where T large T is the search space. Then if we of course there is just some cost values which are measured by neural network in this case. But anyway, when we just pick the best for each pixel, it's going to be like this. So which is the result of the winner-take cost, or just called the WTA. So middle one is the result by Siamese model, or Siamese model. This one, a correct version. And this one is output of the standard block matching like by JNCC or SSD. As you can see here, learning-based model shows a much better performance compared to the standard block matching method. In other words, for example, like such as say load region or the other thin object, it's much more free comparing to the the standard block match often suffer from the some artifact or the errors, but the CMS network provide a much better experiment thanks to the data-driven data-driven approach. Right? And I just give some optimization, but semi-global matching is kind of optimization or post-processing. So as we discussed in previous slide, by applying the left-right consistency given such output, then apply the post-processing, which is called SGM or the semicolon matching. Then your left image disparity or right disparity. Finally, it's going to look like this, which is much better compared to this winner-taker performance. So which shows the importance of the post-processing in the star matching pipeline. Anyway, so this is MCCNN star matching by training the convolutional neural network. Runtime, original version implemented in the CUDA and Lua or 37, so before the PyTorch library. Run on the NVIDIA GTX Titan GPU. Training takes 5 hours. For the 45 million training examples, 16 epochs was considered. So-calculated design with a batch size of the 128 was used. Inference for the single pairs of images takes 6 seconds or the 100 seconds. 100 seconds and 95 seconds for the neural network. It depends on the architecture, like 그죠? A great one and fast one. I mean, a great one require, let's say, 95 times more computation time, and 3 seconds is required for semicolon matching or the SEM, when 1 second is needed just for the cost segregation, but I'll just skip this one. Right, so this is kind of MCNN. So CMS network, I'm the first learnable learning-based model for the matching problem. Alright, so from now on, let's talk about the special regularization during matching. The question was, when will local matching fail like MCCNN or the block matching? So here was the underlying assumption. Corresponding region in both images, I mean the left images and right image, should look similar. This is just underlying assumption. And non-corresponding region should look different. So it was kind of positive pair or negative pair. But when will this similarity constraint fail? Even though we perfectly train a convolutional neural network. Like this. This is very, very frequently find it or frequently found failure cases. So for example, even though these three patches are different patches, but when you enlarge such patches, they seem similar. They look similar because of these patches patterns are repeated. This is one very well-known problem. Or as you can see here, when we just consider the patches here, this is just a no textureless surface. So there's whole of the pixels just like the constant value. What about this? When I just consider the say thin object or the depth boundary or depth discontinuity, this is corresponding left patches or this is corresponding right patches because these patches contain depth boundary. Let's say depth boundary. Even though these two patches are ideally positive patches, but appearance are exactly different. I mean due to this background part. So this is due to the occlusion from stereo setting. So stereo matching setting. What else? Something like this, like the non-Lambertian surface, like as a mirror, for example. So, I mean this as a mirror images depend on, I'll say, few directions. So it means that left image patches and right image patches should be, I mean maybe different each other in the case of non-Lambertian surface. Right, so that is very frequently find it failure cases. Then, how can I solve this problem? How can I solve this problem? The solution is because this is not even though this is not also golden rule. Special regularization is one of the solutions to solve this problem. First of all, how does the real world look like? So this is kind of ground truth experiment. As you can see here, depth information varies slowly, like this, except for depth boundary, for example. So, in other words, depth varies slowly, except at object discontinuity, which are sparse. So, when I just draw the histograms of the depth gradient, this kind of depth gradient, most of pixels are low gradient. It means that they are homogeneous in most cases because the y-axis is a low scale, and object is continuous. These are very sparse. So it means that giving depth smoothness is kind of good solution. I mean, good choices to improve the performance in such cases. So this is the intuitions of the what's that? Right, special regularization. So let's ignore this part. So to explicitly give special smoothness in previous papers, I mean the conventional paper, they just define the MRF, Markov random field, on a grid, which should be pixel in our case. Then, so first of all, macro random field is kind of the graph. So this one is going to be node, and this one is going to be edge, which define also graph. I mean the connectivity, connection between the node. In our case, node should be pixel. Then this one is going to be our, I'll say, target. In our case, it should be this very. So in this kind of graph is called the Markov random field. So there are so many kinds of optimizer to find the best disparity, the optimal disparity while considering the connection between the nearby pixels. So, first of all, given such a Markov random field, solve for the whole disparity map D at once. In other words, MAP solution is equal to minimum of the energy on this Markov random field. So in other words, P of D is equals to exponentials, because this is energy, so exponential of negative sum of the pi theta di, the matching cost at disparity di. Then this term define smoothness between adjacent pixels. Like, let's say if this is I, then this 4 neighborhood, the other pixel, it's going to be J. So this smoothness term just define smoothness between adjacent pixels. For example, in Potts model, the smoothness term determined by something like, I'll say, just a binary map. When t is not equal to t prime, it should be 0. If t is equal to t prime, it should be 1. Sorry, if t is equal to t prime, it should be 0. Or if t is not equal to t prime, it should be 1. So to minimize such a function or such a model, we can just make a smoothly varying depth map. Or when we just consider the truncated model, let's say truncated arrow model, pi smooth of the t and t prime is going to be mean of absolute t minus t prime with tau. And this one is just like the matching cost itself, measured by MCCNM, for example. Because this is a graph model, so by multiplying MRF solver, solving MRF approximately using the pre-propagation, then finally we will have a good corresponding disparity for each pixel while considering the smoothness between the nearby pixel. So this is kind of MRF. So this is a result. This is the inference of the stereo MRF comparing to the, where is that? Yeah, just winner taker case, for example, like this. By multiplying global optimization, like the stereo MRF, we can easily achieve the specially smooth disparity map or depth map. This kind of stereo MRF. Or in another paper, another approaches, because the in this case, if you're interested in some specific object like the car, for example, then if you have a 3D car prior, by just fitting some kinds of the 3D car model to the image space, we can just give some special smoothness by considering such a, I'll say, explicit 3D model. 3D prior. This is another kind of special regularization. Alright, so that's it. So it was MCCNA or spatialization. The last one is end-to-end learning. Of course, after some kinds of deep learning evolution, most of the convolutional network or the computer vision technique has been formulated in an end-to-end manner. End-to-end manner means from the input images or from input to the output, hold the part that formulated in a learnable module, then they are trained with in single training setting. So this is called in end-to-end the network. In TISPNet, which was proposed in Loredi dataset to train convolutional network for disparate optical flow and sim flow estimation in CPR 2016. TISPNet was first end-to-end trained the deep neural network for stereo or optical flow. We'll talk about this one later. To sum up, when you just consider the optical flow input, this net is going to be flow net. But if these two images are left and right images, it's going to be the stereo matching network. It's going to be this net. It used UNet-like architecture with a skip connection to retain the details. Compared to the just correlation layer, I mean the just UNet architecture, they just have the some kind of correlation layer. Correlation layer. In correlation layer, just compute the correlation. Just compute correlation. For example, this is kind of optical flow case, but when we just consider the depth or stereo case, given two patches from the left image and right image respectively, for the just single feature map, this single feature map, by considering the search range, we can just compute cost map. In this case, H by W by T, for example. Then just encode such a cost map with a convolution and decode with another convolution map, a convolution layer by to alive final disparate map. Such a disparate network architecture. Of course, they propose some kinds of technique like the multi-scale training or curriculum learning or whatever. And in this paper, they just use a synthetic data set. It's not a real data, but because this is graphic, this is generated data by graphic engine, something like this. So this, in this case, this image quality is really high, and disparate map, current disparate map are very accurate compared to the real one, like the Kitty data set. So in this display, they just pre-train the model on the large synthetic data set that is cheap to annotate, and just fine-tune on a little real data set like the Kitty data set, because it is very, very expensive to annotate. So this is the pre-training and fine-tuning paradigm in stoichiometric problem. So anyway, so this is the result of the TISPNet. So this is the just left images, and this is the left disparate map. Comparing to the previous, I'll say, pioneering work, TISPNet output is much better. Was much better. And after this paper, there have been so many kinds of other end-to-end learning method, for example, like the GCNet, end-to-end learning of the geometric and context for disparity, deep stereo regression, which was called the GCNet. In GCNet, calculate disparity cost volume. Calculate cost volume. Similarly to the DISPNet, this is going to be the cost volume, whose size was h by w by t, for example. Then, rather than considering just the 2D convolution in GCNet, they started to use 3D convolution. So in other words, calculate the disparate cost volume and apply the 3D convolution on it. So 3D convolution means in original 2D convolution, we just considered the convolution across the h and w axis, but in 3D convolution case, we consider h by w by c, then convolve not only spatial direction but also disparate direction. Then we can more effectively considering or the encode cost volume information. So, and then convert the London match cost C of the t to the disparity via the expectation, like the softmax of the negative c theta of t. C theta of t is just output of the network with the parameter theta for the disparate t case, the disparate candidate t. So we can just consider this is kind of probability at disparate t. Because we considering t is equal to 0 to the large t, by aggregating whole possible t with the probability pt, then we finally find this term. It's going to be our final disparate map. So it was slightly better performance but large memory requirement. So this is kind of stereo images, and this is output of the such a GCNet. Anyway, after these papers, there have been until now been so many kinds of revolution in serial matching pipeline, but let's stop here. So if you are interested in, so please check the Kitty or for example Kitty or such a synthetic dataset website to check the more recent one. Okay, alright, so this is the end of this lecture 4. So yeah, thank you. And because this is recorded video, so we didn't receive any question, but if you have a question, please send an email. Okay, thank you very much. Right, so let's get started. So this is lecture 5. The title of this lecture note was coordinate-based neural networks. So this is about the impulsive function for representing the 3D field. The comparing to the previous lecture note, it was like the point cloud representation or the dense depth representation. So from now we will talk about how to represent the 3D field with a neural network. Okay, so this is the contents of this lecture note 5. So yeah, let's just ignore the number of this content, and let's see. First topic was the first topic will be impression real representation. Second is how to formulate a rendering or full rendering in a differentiable with a differential function. And third one is going to be the neural radiance field, or just called the nerve. And finally, we will talk about how to formulate this nerve in a generative manner. Okay, so first topic is the implicit neural representation. Okay, so this is a traditional 3D reconstruct pipeline. We just assume we have multiple images that take the same scene. And in lecture 3, we discuss how to recover the camera parameter consisting of the intrinsic parameter and extrinsic parameter by using the SFM, for example. Then we also discuss how to reconstruct the depth information from the two view or the multi-view images, and then by how to say back projecting this depth map to the 3D field, it's going to be the full 3D construction. So this is just a traditional 3D reconstruction pipeline. Of course, this is very powerful, and for example, CoNAP method has been still used in many computer applications, even in modern 3D computer vision application. So today, compared to this traditional 3D concept pipeline, today's topic is, can we learn 3D construction problem from the data? I mean, how can we formulate 3D concept problem within a data driven approach manner? So this is today's topic. Right, so because we are interested in the 3D 3D reconstruction by learning. First, we need some large-scale 3D data. Of course, there have been so many kinds of 3D data consisting of the, let's say, very simple object or some kinds of specific class like a chair, or some kinds of room scale images or the 3D space. And the next question is, what is a good output representation? What is a good 3D representation? Okay, so let's talk about how to reconstruct 3D field from the 2D images, for example, or 2D single images. So similar to the previous, many kinds of learning problem, we can just formulate the mapping function from the input images to the 3D field. Of course, this is going to be the neural network because this is very powerful mapping function. So to formulate such a learning problem, we have to define the 3D representation. So there have been several kinds of representation, powerful representation. First one is a voxel. Voxel representation is discretization of the 3D space into the grid, similar to the 2D image representation. Something like this. When you just project the 3D field to the 2D images or 2D grid, voxel representation just discretize the 3D field as a set of the sequence of the some regular grid or the tensor, for example. This is the examples of a 3D voxel representation. Of course, it seems like the quantized representation. And as you can easily expect, this is very easy to process with a neural network because this is a regularly defined grid. But it requires a cubic memory because it has a three-dimensional x and y and z direction. So the order of the memory should be O of the n square n to the third, because the where n is the number of in this case grid, so it's going to be n to the third. So it means that it's really hard to represent the high dimensional or the highly detailed 3D representation. It has a limited resolution problem, and it also based on the Manhattan world bias. I mean the Manhattan world assumption. It means that the scene or the 3D world can be well represented by the a set of the grid. The regular grid. So this is a box representation. Another representation is a point or the point cloud representation. So this is another discretization of the surface with a 3D point, not just with the grid representation, with a 3D point. It does not model connectivity or the topology, just represent 3D point, let's say 3D point position, for example, x and y and g. We need to also assume it defined on the world coordinate, let's say world coordinate. So this is the point cloud representation. So as you can see here, it also, this kind of representation is limited to represent the numerous number of the point. So to represent complex 3D object, we have to limit the number of point, because the number of point directly proportional to the memory consumption, right? Anyway, this is very simple and straightforward representation. Another representation is a mesh representation. Mesh representation is the extension of the point cloud representation. This is also discretization into the not only vertex, the point dust position, but also with a face. Because so let me show you the example. So if we have some vertex like this one, and this one, for example, this is a vertex, and compared to the point cloud representation, it also has some kinds of connectivity between such vertexes, because this is the kinds of the graph representation. So it means that when it's just considering the say this triangle between these 3 points, we can just get the surface, let's say surface. So this is called the face. So it means that compared to the point cloud representation, from now we can represent the say surface by considering the face of the vertices. So this is a mesh representation. Consoles, it also has a limited number of vertices and granularity due to the limited memory. It often requires the class-specific template like the shape of chair or shape of car or something like that, and it may lead to some step intersection in 3D representation. Anyway, so mesh representation is the maybe the one of the popular used representation before the nerve revolution. But today we will talk about the implicit representation. The key ingredient of the implicit representation is it does not require any discretization. So for example, let's suppose that we want to represent such a space. And let's suppose that this surface consisting of the infinitely many number of points. In implicit representation, rather than representing each point or each pixel or each vertex explicitly, just learn some function, let's say f theta with parameter theta, then such that f theta of the p, let's say p was the just position, the f theta of the p is going to be some value, let's say tau. So if this function, let's say f theta, is ideally can uh, estimate the occupancy of the 3D field given just a specific point P. Ideally, with such a function, let's say f theta, ideally we can we can estimate infinitely many point representation. So this is the key ingredient of the implicit representation. Comparing to the previous explicit representation, it only required learnable parameter theta, so which of course much smaller than the explicit representation. So process is it represents arbitrary topology and resolution, and it requires low memory footprint, and it's not restricted to the specific object class or the same class. So this is the implicit representation. So nerve, neural radiance field, is a kind of the implicit representation. We will talk about this one later in this lecture note. So this is implicit representation. This is the kind of coordinate based network. So this is the topic of this lecture note. So the one of the popularly used implicit function in 3D field was the occupancy network. So occupancy network has been proposed in this paper, Occupancy Network Learning 3D Representation in Function Space in CVPR 2019. Key idea was it does not represent 3D shape explicitly. Instead, consider surface implicitly as a decision boundary of the nonlinear classifier. So let's just suppose that here is a 3D model. Can you see 3D model? And when we just project such a 3D object to the 2D plane, it should be like that. And when we just assume this black line as a surface, let's say surface, then if we consider this surface or this line as a decision boundary of the nonlinear classifier, because we can just consider the inside of the surface, the inside object as a negative class, and outside of the surface as a positive class, for example, then this problem is going to be the binary classification problem itself, right? So it means that if we have a good nonlinear classifier to classify such a negative point and the positive point, or the point inside of the object or the outside object, maybe that nonlinear classifier is going to be the direct way to represent the surface of the object. So this is the idea of the occupancy network. So in this paper, they just defined the f theta, where the theta was parameter and f theta was the kind of neural network. This neural network takes the 3D point in world coordinate, for example, x, y, z, and condition, for example, images. If you want to reconstruct 3D field from the images, for example, then and it generates the occupancy probability. Occupancy mean in this case, occupancy is just like let's say this point is object or not. That this object is occupied or not. So because during the training we already know the ground truth occupancy field, then we can find out optimal parameter theta that explain this mapping relationship between the 3D point and condition to the occupancy probability. So in other words, after training the function f theta, model occupancy field. Ideally, after training, the f theta it's going to be the 3D representation itself, because with this etc we can represent or reconstruct infinitely many points with condition, let's say, for example, like images. Other possibility is going to be sine distance function. For example, sine distance function is similar to the occupancy field, but sine distance function is just say, let's say just the distance from the decision boundary, for example. Because if we know the surface explicitly during the training, we can just represent distance, let's say distance from a surface itself, right? Then with a neural network, we can directly estimate the distance from the surface. So this is the another kind of output. So this is called the sine distance field, but the key ingredient is exactly the same to the occupancy field. Anyway, so this kind of work is the starting point of the was done or was the starting point of the implicit neural representation, implicit 3D representation. So this is example. This is the detailed network architecture. So in this occupancy network, for example, we just assume we have a imperfect, or let's say imperfect or partially measured 3D representation. Let's say mesh representation or point cloud representation, or just like box representation. In this implicit representation, by taking such imperfect representation as an additional condition, we want to design neural network, let's say f theta with parameter theta, given some point, let's say x and y and g, for example, like the original 3D point. Then just output the occupancy value given such an imperfect or input 3D representation as a condition. Then within this model, the learner module, it's going to be the theta. So it means that during the training, because we already have the mapping relation between the XYZ to the occupancy value, then we may find out optimal parameter theta. So it's going to be the learned occupancy model. I will just skip the details of the CBN or some kinds of the beta and gamma. So if you want to know detail, please check this paper. But in this lecture, let's say this is the kind of neural network. It's a kind of neural network that contains some lower parameter theta. Okay, so to train such a model, we have to define a training objective, because during the training, we already have some 3D representation, something like the point cloud, for example. So for training, just sample K 3D point cloud from the whole point cloud representation. In this equation, I is the ice patch, because this is the objective function. then J means index for sampled point, sampled 3D point. And what else? G is the latent vector from, for example, from the here. Then O is occupancy. Because occupancy as a training data, occupancy is going to the binary class, binary label. So it's we can just define the similarity between the output of the mapping function and occupancy, current occupancy, as a PCE, cross-sector loss, because this is a binary classification problem. Ideally, this function is enough. This loss function is enough to train a parameter theta. But in original paper, they additionally design KL divergence loss given. Wait a second. Where is that? Given prior distribution. Because our 3D representation can also be used for learning probabilistic latent variable model, not just directly learning the let's say occupancy itself. Just introduce the latent vector G, then apply the KL divergence loss between Gaussian distribution of the latent vector G, represented by mean and variance, then prior distribution. So this is also a loss function. Okay, so this is the occupancy network. So there is one more technique, multi-dimensional surface extraction. So the high-level idea is just apply such occupancy network in a coarsified manner, but I just skip this one. So anyway, so this is the examples of the occupancy network. So this is original input images. Of course, this is a single images, and this is the single image to voxel representation by using the deep neural network, and this method was designed to actually estimate or generate a 3D point cloud from the image input images, or this one is a pixel to matches. Let's write that here. So this one is going to be image to voxel, and this one is going to be image to point cloud, and this one is going to be image to messy, and this one, this occupancy network, directly learning the mapping function from image to neural network, which was the F theta. This is occupancy network, and this is kind of coordinate-based neural network. 자, 여기까지만 간단하게 서머리만 한국말로 빠르게 하고 다시 넘어올게요. 그래서 요 강의 자료는 이제 우리가 코디네이트 베이스드 뉴럴 네트워크라고 하는 개념에 대해 얘기를 하고 있고요. 그래서 이게 왜 해야 되느냐, 이 얘기를 왜 하고 갑자기 나오느냐라는 질문에 우리가 지금까지 얘기했던 SFM이나 스테레오 매칭 같이 이제 어떤 익스프리시트하게 이제 3D 필드를 찾아내는 기존의 트레디셔널 방법들에 대해 얘기를 했는데, 사실 이제 우리가 이제 러닝 시대에 살고 있으니까 어떤 데이터로부터 3D를 리컨트할 수 있는 방법이 있을까에 대한 질문에 대한 답을 찾아가는 여정이라고 보시면 돼요. 그래서 먼저 이걸 하기 위해서는 3D 데이터가 있느냐, 있죠. 이제 뭐 신레벨이든 오직 레벨이든 3D 데이터는 있고, 그러면 어떻게 하면 3D를 나타내는 좋은 레프레젠테이션이냐 라는 질문에 대한 답을 해야 되고요. 결국에 복사는 아주 제일 간단한 방법이었는데, 우리가 지금 보면 3D를 표현하기 어려우니까 2D로 표현할게요. 여기서부터 표현했는데, 그냥 그 공간을 우리가 어떤 그리드로 나눠서 그리드가 채워져 있느냐 채워져 있지 않느냐, 그쵸? 바이너리로 그냥 표현을 해내면 그 공간을 충분히 잘 쪼개면 이런 식으로 3D를 표현할 수 있겠죠. 근데 물론 공간을 쪼개는데 한계가 있죠. 왜냐면 얘는 그 공간을 쪼개는 개수의 3승으로 메모리가 필요하니까 어떤 블락키하게 결과를 쪼갤 수밖에 없다 라는 문제였고, 포인트 클라우드는 어떤 서피스가 있을 만한, 즉 오브젝트 있을 만한 공간을 그냥 포인트들, 어떤 set of the 포인트로 그냥 표현을 해버리는 거고, 그 포인트에 그냥 좌표를 저장하고 있으면 되겠죠. 그렇죠? 그렇기 때문에 어쨌든 우리가 이 포인트라는 특성상 어떤 그 오브젝트를 완벽하게 표현할 수 없어요. 그렇죠? 그냥 아무리 포인트를 늘려봤자 무한히 늘릴 수 없을 테니까. 그래서 이렇게 보면 sparsely represented 할 수밖에 없고, 결국에 이 포인트의 개수 또한 리미트 될 수밖에 없다라는 특성도 있고요. 말 그대로 set of the point이기 때문에 포인트들끼리 어떤 토폴로지, 그러니까 연관성, 그러니까 커넥티비티를 전혀 알 수가 없죠. 그래서 이제 나온 게 메쉬인데, 이제 메쉬는 어떤 벌텍스로 표현되는, 그러니까 3D 모델 자체를 그래프로 표현하자라는 거였고, 이 예를 들어 이런 오브젝트가 있으면 얘들을 다 포인트들과 이 벌텍스들과 그 벌텍스 엣지들을 우리가 사전 정의를 해놓으면, 그쵸? 그러면 그 엣지들만 찾아내면 결국에 뭐겠어요? 이 포인트들과 엣지들을 연결하면 어떤 서피스들이 나오니까 다이렉트하게 그 서피스, 그러니까 오브젝트 서피스까지 표현할 수 있겠죠. 그래서 사실 메쉬가 가장 많이 쓰였던 표현들이고요. 근데 이제 이러한 표현법들은 다 3D 필드를 어떤 익스프리시트하게 벡터나 어떤 텐서 형태로 계속 표현을 해야 되니, 어찌됐든 이 무한한 스페이스의 3D 공간을 디스크리타이즈 했다라는 데 한계가 있다. 그래서 이제는 노 디스크리타이제이션을 필요로 하는 이 임프리시브 펑션 같은 경우는 어떤 펑션인데, 무슨 펑션이냐? 코디네이트 픽셀 P, 3D 포인트 P, 어떤 코디네이트 자체를 받아서 그 코디네이트에 오브젝트가 있는지 없는지, 즉 아큐판시를 바로 배틀할 수 있는 뉴럴 네트워크를 배워버리자, 매핑 펑션을 배우자라는 아이디어였고요. 즉 f theta of the p is equal to tau 라고 하는 이 펑션에서 이 세타 자체를 배워버리자라는 개념이죠. 그래서 이 f 세타를 어떻게 정의하느냐를 가지고 이제 지금부터 많은 얘기들을 할 건데, 그냥 간단하게는 이 어떻게 정의할, 이 먼저 인풋은 그냥 3포인트로부터 그냥 occupancy probability가 바로 나오면 되는데, 만약 내가 이미지 to 3D 가고 싶으면 그냥 이미지 컨디션을 추가로 받으면 된다. 또는 내가 포인트 클라우드를 가지고 이걸 3D 임프리스 레퍼런트 하고 싶으면 그냥 포인트 클라우드를 어디션 레퍼런트 받으면 되고, 그 인풋들을 가지고 아웃풋 베터에는 뉴럴네트워크 배우자라는 개념이죠. 그래서 이제 뭐 그런 대표적인 예토가 이런 아큐판시 네트워크 얘기를 했고, 이걸 학습하려면 뭐 가장 간단한 로스는 이제 BC로서 있으면 돼요. 그래서 아큐판시를 우리가 바이너리로, 이 포인트는 실제 트레이닝 데이터에서 오브젝트 안에 있었냐 없었냐를 바이너리로 갈고 그거를 바이너리 클래시피케이션 학습시키면 된다. 그럴 때 BC를 쓰면 된다. 근데 이걸 조금 더 베리에이션으로 하기 위해서 확률적 관점에서 이 레이턴트 스페이스로 배워내게 하고, 그러니까 레이턴트 벡터 G로 배워내게 하고, 이 G 자체를 어떤 평균 분산을 배워내게 하면 조금 더 확률적으로, 그러니까 프로버티가 배웠기 때문에 조금 더 저 모델 자체를 스무드하게 잘 배울 수 있겠죠. 뭐 그런 특성이 있긴 한데 이거 뭐 넘어갈게요. 그래서 뭐 디테일은 여러분들이 논문을 보시면 될 것 같고, 그래서 이런 아큐파시 네트워크가 있다. 그래서 이제 아큐파시 네트워크를 썼을 때 이미지 to 뉴럴 네트워크, 이미지 to 인프레시브 펑션이 가장 디테일을 살리고 오리진 이미지를 잘 복원해내더라 라는 여기까지 했죠. 오케이, 여기까지 하고 또 넘어가 보면 another aspect during reconstructing the 3D world should be not just geometry surface like this, but also material or the lighting information. So for example, given a input images, of course this is a real images, so taken under different illumination or the other lighting condition, and given 3D geometry, like massive representation or the implicit representation in this representing material and lighting condition. It's going to be like this. In this problem definition, given image and 3D geometry, by using the neural network, we want to manipulating the illumination or changing viewpoint. So we want to say model lighting condition or the illumination. So how to do this? How to model continuous surface light field? So to do this, we have to consider the PRDF. So PRDF, okay, so it was the topic of the lecture 2, lecture 3. lecture 2였어. lecture 2. So this is the texture of the image. The input image. Okay. So 3D world was projected to the 2D images. Of course, we have a color images, so it means that the color value can be modeled by the such a function consisting of PRDF, PSV. So P was kind of 3D point, and L was a light setting or the direction of the light source, and V was a viewing direction. Then, if your neural network can estimate color value directly given point P and light source L and V, then this neural network can model 3D color representation or the textual representation. In other words, comparing similar to the geometry representation. So this function, let's say light field representation, just take light source. In this case, point representation, x, y, z, and v direction, just 3D vector, and Rm, where Rm represent light setting. Then this neural network can directly generate a color image. So this is kind of the light source representation with the neural network and implicit representation. Something like this. For example, let's suppose that you have an input shape, input 3D structure. Then let's suppose that you have input images taken under a different viewpoint. What you want to do is by considering such observation, in this case, so single image, for example, just extract the picture vector. Let's say this is input image encoding G. Then in conditional implicit surface light field, just design the neural network or function that take this image embedding G. Then geometry encoder S from the geometry encoder output, let's say shape encoding, and 3D point cloud that we want to know the appearance value. So it depends on how we design such a appearance representation. But in this problem, in this paper, they just represent d-dimensional vector. Then in lighting model, of course, this is another kind of neural network. Just take light setting and beam direction, then directly estimating the 3D pixel, 3D color. For example, for given this one. So for example, if we know x, y, g as a location of the 3D point, then this one is going to be the color, let's say RGB of the 3D in the 3D space. Of course, during the training we know the target images by directly comparing the reconstruction loss. We directly train such a appearance network and the lighting model. So this is kind of lighting field modeling with implicit neural representation. Yeah. Another aspect is the represented motion, but I will just skip this one. And lastly, what about scene? So far we just discussed how to represent object, but we are not only interested in the object, but also other scene level property like the background of the object, for example, like indoor scene. So, because the scene level and the scene 3D representation is also kind of 3D representation, of course, implicit representation can be used to represent the scene representation as well. Of course, occupancy network, for example, also can be used to represent the scene level representation. But limitation was okay, let's go back to the structure of the implicit neural representation. Given input x, it was going to be so it's going to be image or input 3D. Then by using some function or neural network, just extract the 1D picture vector. Or we can just call this is a 1D encoder or this 1D feature vector, or this is going to be global latent code. Let's write that. Okay. So let's say this is the global latent code, which is just the 1D vector. So we just assume this 1D vector contain most of information of the condition or input x. Then okay, so if we just assume this 1D encoder is a pi function phi, then this feature, let's say pi of x, and 3D location, let's say p, are going to be input of the some neural network or the FC or neural network, which generate the occupancy probability, let's say f zeta of the p comma pi x. So this is the high level structure of the implicit neural representation. If you are interested in very simple 3D like the simple object, it works well because this global latent vector contain most of, simple object information. But if you want to represent the scene level 3D world, because this global representation does not contain any local detail or local information, and it just contain overly smooth geometric information. So generate the 3D field is going to be very blurry. So this is examples of the occupancy network to generate such a complex object, like the indoor scene, for example. In other words, so like this. So 3. Where is that? 3. So implicit model like the occupancy network work well for simple object, but poorly on complex scene, because they want to extract, they want to encode most of conditional information to the just simple 1D vector. And so thus we just lose some local details of the content information. So that was the bottleneck of the occupancy network. Alright, so how can we overcome such a limitation? So let's go back to here. If this function just contain globally varying information, direct solution or direct way to overcome such a limitation is just like augment such a feature vector to contain locally varying information. In other words, if this feature, this pi function can take not just input x but also pixel isolated location p, then this feature is going to be thus a locality aware feature map. So this is some key idea of the convolution occupancy network. So convolution occupancy network has been proposed in ECCB 2020. It was very simple. So for example, if you are interested in representing the imprecise 3D world from such a sparse point cloud, for example, this sparse point cloud is going to our input. So rather than just project such a point cloud information to the 1D vector, so in convolution occupancy network, in 2D plane encoder, for example, just encode like this. So in 2D plane encoder part, first of all, there is a very powerful point net neural network that process the point level irregular data with the neural network. So first of all, encode some feature map by using the point net kind of encoder. So it means that each pixel, each point can be the vector, some kind of vector, like given x, y, g, for example. Then after point nav, so each point x, y, g can be some kind of vector. Let's say let's suppose that let's just say this is just vector vector. Then to represent the local information in such a feature point cloud are projected onto the canonical plane. So because we're interested in 3D information x and y and g, we have a 3 canonical plane, xy plane here, and xg plane and yg plane. So for example, for xy plane, such a point cloud information is just projected to this 2D feature plane. Then it means that from now on, this is going to be the 2D feature map. Then we can directly multiply 2D UNet or 2D convolutional neural network to further encode the 2D feature information. Similarly, we can apply the same operation to the YG plane, then apply the 2D UNet and project it to the XG plane, then apply with processed by the UNet. Then finally we will have a 3 feature flag, 3 2D feature flag, 3 2D feature flag. So try feature flag. So comparing to the just 1D vector in original occupancy network, because this feature map, not just feature vector, feature map contain the local information. So if you want to decode some point pixel P, three location P, given such a feature map, try feature map, if we were interested in pixel P, 3D location P, by using Bayesian interpolation, we aggregate this information, and this information, and they are transferred to the occupancy network or just a neural network to estimate occupancy value f theta of the p comma pi px. Because the in this scenario 2D convolutional model has been used to encode a good dry feature representation. So this kind of work was called the convolutional occupancy network. Yeah, so this is just a simple one. This is a simple one. So if we want to directly encode the 3D information rather than just considering the projection and 2D convolutional neural network, in another variant, we can directly apply the 3D convolutional network to the 3D feature volume. Then this 3D feature volume with this 3D feature volume, so locally varying pixel P, locally varying feature pi of P comma X can be directly extracted from this 3D feature volume by using trilinear interpolation, because this is 3D representation. Okay, so so in this variant, 3D volume encoder in 3D volume encoder local point net process input and volumetric feature encoding is applied, and in 3D volume decoder, original 3D feature volume is processed by the 3D unit and create the feature via trilinear interpolation, because this is a 3D volume like the box representation. Then, of course, we require the shallow occupancy network f theta. So, in comparison of the occupancy network and convolutional occupancy network, of course, we require some neural network, because this is an implicit representation. But in occupancy network, we just project or the input data to the 1D vectors, so we lose some kinds of local detail. But in convolutional occupancy network, we extract some locally varying feature map. Then your features, it's going to be, the feature going to be aware of the 3D location, let's say P. So this is occupancy network versus convolutional occupancy network. Okay, so this is examples of the object level reconstruction by using convolutional occupancy network. Comparing to the occupancy network, this is occupancy network. This is convolutional occupancy network. Comparing to this one, convolutional occupancy network achieved the higher accuracy and faster convergence, because it can use the inductive bias of convolution module and better preserve the local detail, like this or this. In a scene level representation or scene level 3D reconstruction problem, ONET occupancy network frequently fail to record the highly detailed complex, highly detailed 3D field because of this is just like the globally bearing representation, but this one, convolutional occupancy network, because highly detailed 3D work. This is a generalized performance because this figure shows the generalized performance because this model was trained on the synthetic room and evaluated on ScanNet, which was real data. So because of this, there was a domain gap. But this convolutional occupancy network still performs a powerful performance. This one. From here to here to here. Last one is for the large scale reconstruction, like the Metaverse 3D. This is a highly large, detailed 3D representation, like the say building or the one floor consisting of the several kinds of room. Let's say here. So because this is a fully connected convolution module, and this is trained on the synthetic cloud and sliding window inference, because it's really hard to directly reconstruct the full 3D world. So it just reconstructs 3D world by considering the, let's say, 3D cube in a sliding window manner. So inference at each in this case tensor how to say sequentially, because it's really hard to represent this large scale scene directly. So which means it scales to any thin size by just considering sliding window inference, even in training. Okay, let's briefly summarize in Korean. 자, 여기까지만 하고 우리 오늘 끝낼 건데, 아주 간단한 한국말로만 정리를 또 해보면, 그래서 이제 우리가 3D 지오메트리뿐만 아니라 어떤 3D 어떤 칼라 정보들도 사실 이렇게 임플리시트하게 표현할 수가 있을 거다. 결국에 무슨 얘기를 하고 싶은 거냐? 그 칼라를 정의하는데 어떤 요소들이 사용되었는지만 알면 사실 그거를 모델링할 수 있겠죠. 그래서 옛날에 BRDF를 떠올려 보면 내가 3D 포지션 P와 비행 디렉션 V와 어떤 S라고 하는 소스 디렉션으로 표현했는데, 우리가 이걸 좀 제너럴라이즈 해서 어떤 L이라고 하는 라이트 세팅을 정의할 수 있다면, 우리가 PVL이라고 하는 벡터를 받아서 칼라 값들 뱉어내는, 바로 3D 공간의 칼라 뱉어내는 뉴럴네트워크 학습할 수 있을 거다라고 하는 개념이고, 실제 그렇게 학습했던 모델이 이제 이런 모델이 있었죠. 이게 왜 중요하냐면, 이제 나중에 널 풀어가면 우리가 3D 지오메트리뿐만 아니라 어떤 텍스처 인포메이션까지 동시에 에스티메이션 해야 되기 때문에 이제 이런 개념들이 중요한 거예요. 뒤에서 좀 얘기하겠지만. 그리고 또 마지막 하나가 지오메트리를 나타낼 때 이제 이렇게 그냥 글로벌 레이턴 벡터로 하나 표현하는 것보다 표현하면 뭐 오브젝트는 적당히 하는데 이렇게 컴플렉스 씬들 같은 경우는 거의 불가능하다. 왜냐? 글로벌 벡터 하나에는 그 로컬 디테일이 다 빠져 있으니까. 그래서 로컬 디테일을 살릴 수 있는 이제 로컬리 베링하는 피처 벡터가 필요했던 거고, 그래서 이제 컨볼루션 오큐pancy 네트워크에서는 뭐 이걸 바로 설명하면 어떤 예를 들어 포인트 클라우드 to 어떤 풀 3D 필드를 가는 어떤 모델이라고 했을 때, 포인트 클라우드 정보를 어떤 3D 피처 볼륨 안에다가 인코딩을 하고요. 어떤 3D 유닛 같은 걸 써서, 그럼 뭐가 되냐? 이 피처 볼륨에서 내가 3D 로케이션 P의 occupancy를 알고 싶다고 쳤을 때, 그 포인트 P를 알려주고, 그 피처를 뽑을 때 그 포인트에 해당하는 피처가 뭘지를 어떤 인터폴레이션에서 가져오고 그 벡터를 뉴럴 네트워크에 넣어버리는 거죠. 그럼 얘가 로컬 디테일들을 보면서 포인트 P에서의 occupancy를 뱉어내게 학습을 시켜버리면 훨씬 이제 디테일드 레프렌테이션을 배울 수 있을 거고, 오브젝트인 경우도 마찬가지고 신 레벨인 경우도 보시면 이렇게 훨씬 더 보면은 디테일한 스트레이 정보를 살리더라라는 게 이제 아큐판시 네트워크에 대한 정보입니다. 네, 여기까지만 할 거고요. So yeah, so this is the end of today's lecture, and after that we will talk about how to design a differential volume rendering and how to design a nerve or neural radius field, and how can we design a generative model for the neural radius field or something like that. Okay, so thank you very much and see you next week, maybe after midterm exam. Thank you.